What is the mass of the sample if the molar mass is 137.922 grams per mole? It cannot be determined. Okay, so what we're going to do here, we're going to use the activity, right? Activity is lambda n, right? And we know the activity, right? And we can figure out the lambda from the half-life. So then we can figure out n. And knowing the number of atoms in the molar mass, and knowing that 6.02 times 10 to the 23rd of those atoms would have exactly this much mass, we can figure out the amount of grams that we actually have, right? So first thing I'm going to do is I'm going to figure out the lambda. Lambda is ln2 over 6.5. And in seconds to the minus 1, lambda is 0.106638, and that's probability per second, the per second probability of a decay. Right, so now we can go, what was that activity? 8.8 times 10 to the 11th. The 11th counts per second, right? Equals 0.106638. That's a pretty high probability, right? 1 in 10 chance. Okay, times n. And now we can find what n is. Okay. 8.8 times 10 to the 11th divided by that lambda gives us n is 8.2522 to the 12th atoms. Okay, and then we're going to divide that by how many you need to make an entire mole, right? So this is going to be how many moles, right? If we had 6.02 times 10 to the 23rd atoms, we'd have a mole, right? But we only got that much. We got just a tiny fraction, right? And this is atoms per mole. And then notice that we're going to end up with moles, right? So divide this by Avocado's number, right? And I get that we don't have very many moles. 1.370, I'll just say 8 times 10 to the minus 11th moles. And then multiply that by the molar mass. Because this is, by the way, grams per mole. Right, so this is going to give us, of course, grams, right? I get 1.89 nanograms. I think that's just funny. 1.89159 times 10 to the minus 9th grams. So 1.89 nanograms. Can you send me a nanogram? That's kind of awesome. Woohoo!